Yeah, I could, actually, I could stand here very erect with the microphone. All right, the next slide we will show that the complement system is designed. I have done that. Literally. So I've tried, first two classes, I've tried really, really hard to put everything in context and give you a sense of that what I'm teaching you makes sense and how it sort of all connects. I have to admit, today's class, I can't do that. There's a lot about chemistry and enzymology in today's class. And it is, the enzymes work the way the enzymes work, and the substrate does its thing, and blah, blah, blah. And I don't know how to put that in any context. I don't know how to give you a feel for that system. It's a series of enzymatic steps. And we just sort of have to fasten our seatbelts. And there's going to be a fair amount of memorization without concept behind it, except it works. And that is what it is for this topic. So complement, I hope it's complement, yeah, sure, that's what I prepared for. Complement, notice the complement begins with has an E in the middle. So there are two complements, an I and an E, and most of us screw up which one to use and so on. The way I remember is complement with an E, the word complete is spelled with an E. And then whenever you're using complement to complete something, this is the complement you use, and you use an I when you're giving someone a complement. So what is being completed? Well, it ends up that years and years and years and years ago, we knew there were antibodies. Scientists, clinicians knew there were antibodies and knew that antibodies were good things. You could take antibodies from one human being and give it to another human being, humans who had traveled to certain parts of the world. This is way back in clinical medicine. The people who traveled to certain parts of the world would, you would get antibodies from them, and you would inject them into people who were about to travel to that part of the world. It was a gamma globulin shot. If anyone even heard that word, it's probably generations ahead of you or behind. Ahead of you, I guess. And therefore, these antibodies mediated protection. Complement comes in because it was found that antibodies were more effective when you completed them, when you complemented them with some other liquid in the serum. So there were, at the time we didn't know it was enzymes, but there were proteins in serum that when mixed with antibody made antibodies more effective in protecting us. That's where so complement, the complement cascade that we're going to talk about today, completed or complemented the activity of antibodies in protecting us. So, get my reason pointer. Is there anything that you can use as a pointer? Is it about the best we'll do if I probably can read with it? No, I can't. Anyway, so a couple messages. You're gonna see this slide 4 or 5 times today. So I'm trying to lay the system out. Now the truth is, the enzymology that we're going to talk about today, it's mostly all proteases, by the way, is actually gorgeous. And if I do a good job, you're going to appreciate that all 3 of these pathways leading to that central green molecule called C3 converts. I haven't defined any of this yet, so don't worry about it. Really are the same pathway, but with different names. Same enzymatic steps are involved, the same biology or biochemistry that's driving the pathway is the same. It's just we have different genes and different gene products that do the same thing. So if I do a good job today, you'll appreciate that. If I don't do a good job, I apologize in advance. There are 3 pathways, yellow, red, and blue. The classical pathway, which is not what we'll start with, was classical because it was the first one found. That's the one of complementing antibodies. You'll notice in yellow, the second box down, the word antibody appears. So the complement system was first found when people added antibodies to bacteria, and you got some death. You added this other liquid plus antibodies to bacteria, and you got a lot of death. Complement system was found that way. It was the classic system. Suddenly, the next one found was the alternate pathway, and ends up the alternate pathway, which is what we'll begin with, is the older one. So the more sophisticated, and then the lectin pathway is the newest. The more, slugs and various plants, horseradish for instance, I can't think of some other plants right now, all have the alternate pathway. So evolutionary, it is the oldest. We're going to start with it because if you understand it, when I add the antibodies to it, I think the antibodies will make perfect sense. And then when I add lectin to the story, that'll even make more sense, and we can build from it. So even though the classic pathway you would think is the oldest, evolutionarily the alternate pathway is the oldest, and it's alternate because of when science is founded. The key point here from this slide is our goal. You know, we talked about endgame on Monday. I'm going to try to use that expression again today and see if it works from a teaching perspective. The end game here is to create this molecule called C3 convertase. Okay? So notice that all three pathways lead to the production of C3 convertase. So I'm going to introduce you to C3 convertase first, and then from C3 convertase, you get a whole bunch of enzymatic steps that follow, listed in all the slides down here, and there are then 4 outcomes. So just out of curiosity, how many people have even heard of complement? How many people sort of think they know what complement might do? So it's really about 3 or 4 of you. Fantastically low. No, that's not a comment on you. It just doesn't help me with my next pedagogical trick I was going to use. So I was hoping happy you would take. For the 2 or 3 people who have heard of complement, tell me please, what do you think complement does? What's the main function of complement? Don't look this up. From your memory, and I'm not embarrassed. I'm not trying to embarrass you.
A certain stimulus elicits a certain sort of lock and key response.
No.
You want to coat the antibody in some sort of protein that helps macrophages, or that attracts macrophages and helps them.
That's awful. So you are right. That is one of the activities of complement. It's not the one I was hoping you would say. So what?
I think the complement is to attach to the invading organisms to make hosts.
And lysis. Yeah. Right. So most people, and me included, before I started teaching complement, I learned complement, 5 or 7, 10 decades ago. Didn't really listen. Actually, that's not true. Actually, I have to apologize. That was a lie. It wasn't a lie on purpose. I just realized. I've never taken an immunology course in my life. Actually, let me go back a step. I've never taken a biology course in my life. I was a physics and math major in college, and I got my master's in physics before I switched to biophysics, where I got my doctorate. So I have never taken a classic biology course. I have no idea what a tree is. My students in my lab now are doing a lot of microbiome work where there's phyla and family and species and genus, and I'm looking across on that stuff. Hold the table. So anyway, so I've never taken an immunology course, so I didn't learn complement years ago. I learned complement to teach this class, or to teach my undergraduate class, which then led to a spin-off of teaching here. So when I learned complement, meaning listening to friends or semi-reading a paper at midnight or something, it is the lysis of bacteria. It is the means by which lysis of bacteria. And one of the 4, I hope it's here. Oh, yeah. One of the 4 activities associated with complement is the lysis of pathogens. And the pathogen is almost always a bacteria. Is there ever a case when it's not a bacteria? I'm thinking. I think it's always a bacteria. So I'll double check on that. But when we get to this point, there are 4 biological activities resulting from this complement cascade. So all the boxes are a cascade leading to 4 biological activities, even though complement is sort of known as the lysis activity, or at least to me it was known. And now we need to sort of say, what is this cascade that I've been mumbling about? So let's talk about the 4 activities first. Cell lysis, that's how complement was found in the classical pathway. You add antibodies to bacteria, and then the antibodies bind to the bacteria, and the bacteria can sometimes get immobile, sometimes they lyse. Not very well. You add this other liquid to the antibodies to the bacteria, and all of a sudden the bacteria explode. That's where complement, the word came from, that's the classical pathway. However, in the process of generating this complement cascade to lyse bacteria, you also generate molecules that, which one is this? Okay. Increase phagocytosis. Phagocytosis, remember about sipping, drinking, and gulping. Phagocytosis is engulfing an organism. And macrophages and neutrophils have phagocytic activity. Talked about that a month or so ago. Opsonization, and complement is basically, involves the process of opsonization, is imagine eating very bland food. You eat it because you eat it. If you add some spices to the bland food, you enjoy eating it. Basically, opsonization is adding some spices to the bacteria so the phagocytes are more efficient. So by coating the bacteria with complement, which means nothing to get, but it will for the end of the hour, by coating bacteria with complement, the little red things, phagocytes are more efficient. So one complement in red can kill, can lyse the cell directly, can eliminate the bacteria because it forms a bridge between the bacteria and the phagocyte, makes the phagocyte more efficient. Remember those cries for help that we talked about on Monday? I talked about 5 cries for help. I left one out on purpose. The 6th one, if you will, is part of the complement cascade. And you will see that there are products of that cascade that also involve activating innate immune cells to bring them into the tissue to have them phagocytically destroy the organism. So it is another cry for help, if you will, and it's a product of the complement system. And then finally, there are these awful things that we form called immune complexes. You'll hear about it in hypersensitivity. There's actually a hypersensitivity disease. I'm not teaching hypersensitivity this year because I guess they screwed up the schedule from what I understand. I told you over the weekend. I picked up on that. But there's a hypersensitivity disease where we form immune complexes. And when we talk about antibodies, I'll describe immune complexes to you a little bit better, but they're bad things. They clog tissue, they clog blood vessels, and they can kill you. So complement is involved through a phagocytic process as well in removing immune complexes. So these 4 activities are the effective function, the final mechanism by which we are protected through the complement system. I will ask a question in the exam for those 4 activities, maybe 2 questions. So just memorize what those 4 activities are. Just memorize cell lysis, opsonization, inflammatory mediators, cries for help, and removing immune complexes. Just memorize those 4 and you got two questions on the exam. Excuse me? Right, so remember we talked about the neutrophils, the eosinophils have mast cells, basophils have granules, and those granules have noxious agents that protect us. The opening up of the cell and the release of those contents of the granules is called degranulation, and these complement proteins enhance that activity. So these are the 4 effector functions of the complement cascade, which are these 4 boxes right here. They're the same 4. They might be worded a little differently, probably different textbooks. But those 4 boxes there are the same 4 that I'll show you on the next slide. Just memorize them. So there are 3 pathways into the complement cascade. I haven't used the word fixation, or maybe I'll use it now. It is a proteolytic. I've been saying enzymatic. It's really a proteolytic cascade, meaning it's a series of proteases. Proteases degrade proteins, or cleave proteins. And the 4 effective functions we just talked about. So remember the 3 pathways in as an exam question. Remember the 4 pathways out as an exam question. And we're going to talk about the cascade now. Okay, so remember from this slide, it's going to show up a lot. Clearly, all those three pathways lead to creating this thing called a C3 convertase. So that's the critical step for all the effector functions to be generated. So who is a C3 convertase? And ends up, oh, do I have, did I do this or did I not do this? Oh, good, okay. It ends up, there are two C3 convertases. Remember I said there's a lot of parallel, that there are a bunch of proteases involved in all these, in this cascade, but really if you can understand it, they're the exact same protease and the exact same steps with different names. So it ends up, part of that message I'm trying to deliver, that there are different names, there are two C3 convertases. I'll introduce them to you first, then we'll get to how you make them. One of the C3 convertases, its name is not on here yet. It's just shown as a scissor. C3 convertase could be called C3 protease because it makes a proteolytic cleavage in a molecule called C3. So in circulation, C for complement, complement proteins are made by the liver. We have high levels, milligram per ml levels of C3 in circulation all the time. C3 in circulation all the time is inert. It doesn't do anything, which is good. Because I've just told you this cascade starts an inflammatory response, and you don't want an inflammatory response if you're healthy. So C3, uncleaved C3 is inert. Please take that sentence and put quotes around it because I just lied to you. So I'll clean that up. I'll clean that up in a couple of minutes. So C3 circulates at high levels. It's inert. It doesn't do anything. That's fine. We want it to be cleaved by this protease called C3 convertase, or protease clipped. And you create two molecules. You create a molecule called C3A that is small, truly small, and C3B. That's our goal. Our goal is to cleave C3, and the mechanism by which we do it is this protease called C3 convertase. And I will tell you in a moment, there are two proteases that are the C3 convertase. So our goal is to create C3A, which by the way is going to be one of the cries for help. So C3A is going to be just like an IL-1, alpha or beta or a TNF or a prostaglandin. It's a small mediator that activates immune cells to get them angry, protect us. C3b's goal is to bind to bacteria. So C3 cannot bind to bacteria, but after C3 is cut into C3A and C3b, C3b will bind to bacteria. Okay? So, who is that scissor, that C3 convertase? I'm not going to do that one yet. That C3 convertase in the alternate pathway, remember we're going to talk about the alternate pathway first. I'm going to give you both now and we'll cycle back. The C3 convertase in the alternate pathway is called C3b-BB. As shown on the right-hand side of the slide. So C3b-BB is the C3 convertase for the alternate pathway. We'll come back to this, but C2A, C4b is the C3 convertase for the other two pathways, but we'll come back to that. Okay, so I just told you that the goal of C3 convertase is to cleave C3 into C3A and C3b. I also just told you, I want to see this slide for a minute. Okay. That the C3 convertase that we're going to talk about first is C3b-BB. Anyone have a problem? Did I just really screw up?
Isn't it having created
By the way, you know my teaching style. Anytime I do something like that, it means I'm trying to start a conversation. Please walk up.
here?
Yeah.
So you said that it is cleaving the C3b, but that it also is the C3b.
Right. C3b-BB is the enzyme that cleaves C3 to make C3b. So how can you have C3b-BB the convertase, available if you haven't made, if C3 is in circulation, you don't have any C3b in circulation. So how do you make C3b, cleave C3 to make C3b, to make the convertase if you don't have C3b there in the first place? Is everyone confused? Because that's what I wanted you to do. I want you all confused or frustrated. So the molecule that is the product of the protease is part of the protease. So we've got an absolute conundrum here that we have to solve. Everyone appreciates the conundrum. I don't care if you have something in your mind of how to solve. I'll solve it. But everyone can appreciate the conundrum. Okay. So you got a lot of head shakes. So now, why do we want, I'm going back a slide. Why do we want to cleave C3? Remember, I said the end game, well, it's right here. That's fine. The end game is that we cleave C3, and we create C3a and C3b. C3a is a little molecule, it's a stimulant, just like cytokines are stimulant, prostaglandins, immune stimulant. Our goal is to make C3b, and C3b binds to bacterial sarcophage. That's where we want to be. Okay. How does that happen? It ends up with C3, which is inert. I've said it's inert, and that's a lie. Clean up the lie in about 2 slides. Upon cleavage of C3 into C3a and C3b, buried in C3 is a thioester bond. Thioester bond is literally the chemistry that you see in yellow, purple, and red. That thioester bond is buried inside C3. It's not available. That makes C3 inert. Upon cleaving C3 into C3b, you reveal that thioester bond, which is our goal. Why? Thioester bonds are chemically incredibly nucleophilic, incredibly enzymatically, chemically reactive, not enzymatic, chemically reactive. And what they like is primary sulfates and primary amines. And luckily for humans, we don't have a lot of primary amines and primary sulfates on the surface of our cells. Luckily for the system, bacteria have a lot of primary amines and primary SH groups on the surface of their cells. So this nucleophile that is revealed upon cleavage of C3 into C3b is chemically very active, and if it finds an SH group or an amine group, an NH group, on the surface of bacteria, it's going to form a chemical link. This is a covalent bond with the bacteria. So we have coded the bacterial, or we have chemically covalently linked C3b to the bacteria due to the fact that upon cleaving C3, we reveal this thioester bond. Thioester bond chemically reactive, looks for primary amines. Those primary amines are on the bacteria. That nucleophile attacks the bacteria. We create a covalent linkage of C3b to the bacteria. That's what we want. Yeah?
Can you mention what that had to do with it being inert?
Excuse me?
Can you explain why the thioester bond had any relationship to C3 being inert?
Well, C3 has a thioester bond in it, buried in the protein,
Is it
but
because
it's
it
not
wasn't
available because of, it's not, it's sort of drawn here like C3A covers it. It's not quite that simple. C3B bends over and covers it. But basically C3 has the thioester bond buried inside, and therefore C3 is inert. When you cleave it and create C3b, the thioester bond is available for that rapid chemical reaction. And you might have, I'll go back to a refresher slide just so you, when you're studying, you have it. Complement fixation, that is the chemical binding of C3b to the bacteria. So our goal here is to cover bacteria with C3b. We do it by cleaving C3, which is inert, with the C3 convertase. We reveal the thioester bond, that nucleophile attacks the bacteria, chemically links C3b to the bacteria, bingo, we're done. That's what we want. Well, we're not done, but that's what we want. Which is really what you're seeing here, without the chemistry. Okay. And this is once C3b is bound to the bacterial surface. Most of my slides say pathogen, but I am 99% sure it's almost always a bacteria. But I'll look that up, and I think I'm with you guys. I don't know when I see you again, maybe Friday, Monday. I'll clean that up for you. That C3b bound to the bacteria allows for the formation of this C3b convertase, which is C3b-BB. I haven't told you what B is yet, but we'll get there. We still have the problem though. How did C3 get cleaved by this guy? Because you need C3b to be this guy, and we don't have this guy around. So we still have that conundrum. And that's solved by good, the tick-over reaction. Here's the lie. The lie I made about 5 minutes ago was C3 is inert. It ends up, it's not quite inert. All proteins breathe. All proteins have a structure, but think about the chemical bonds of all the structure, the van der Waals forces, the ionic bonds, so on. They're constantly changing. They're breathing. They're moving a little bit. C3 breathes as well. Every once in a while, C3 will breathe to a point where the thioester bond is revealed. I said that C3 is inert because the thioester bond is buried inside, and that's true. But rarely, or once in a while at least, that thioester bond is revealed, not because of cleavage, which is what I showed you on the previous slide, but because C3 breathes. When that thioester bond is revealed, when C3 is cleaving, is breathing, that thioester bond wants to nucleophilically attack something. Okay? Yeah?
What do you mean exactly by breathing?
I'm sorry?
What do you mean exactly by breathing?
The structure is changing. It's flexing. Maybe flexing is a better word. The protein is not, if no protein is this shape and never, or this shape for the rest of its life. A protein is this shape, and then it's this, and then it's back and forth. So it's flexing a little bit. Every once in a while, that flexing reveals the thioester bond. That thioester bond is now there. What's it looking for? It's looking for a primary amine or an SH group to bind to. Let's go to the healthy person first. If you're healthy, C3 flexes. I won't use 3, I'll use flex if that works better for you guys. C3 flexes. Thioester bond is available. Thioester bond, nucleophilic, wants to attack primary amine and SH group. You're healthy, there are none around. What happens? What happens is, we're going to go back a slide. In the healthy individual, that thioester bond through a nucleophilic attack attacks the water, which is obviously the liquid that we live in. Once that occurs, that thioester bond is cleaved, the chemical reactivity is gone, and C3 bound to water is just a wasted molecule and it will be destroyed. So when you're healthy, so we've got this flexing of C3b. Remember, we still have the conundrum, how do we make C3b-BB, which is a convertase, when we don't have it around yet? We need to have it around to cleave C3, that's the conundrum. So I'm solving that conundrum for you through this tick-over reaction. So the flexing of C3 reveals the thioester bond. When you're healthy, the thioester bond nucleophilically attacks water. Bingo, you end up with the molecule up top, and that molecule just gets destroyed. And we do this at a very, very low rate. If you're infected, if you're constantly doing this flexing and every once in a while revealing that thioester bond, if you happen to have a bacteria in you, that flexing is going to occur near the bacteria, just like it's going to occur everywhere else. That thioester bond is going to be available near the bacteria. That nucleophilic attack can occur, and C3b will be deposited on the bacteria by chance once in a while due to this random flexing of C3 revealing the thioester bond. So we get C3b on bacteria due to, if you will, the low, not the low, because of the low level availability of that thioester bond randomly throughout the body. Does everyone get this? Because I can't go on. I can go on, but it would be fair to you if people don't get it. Anyone in trouble? Okay, that's called the tick-over reaction. The reason it's called tick-over is because C3 is flexing randomly. Every once in a while the bond is there. Most of the time that bond attacks water. The thioester bond attacks water, everything's fine. Once in a while it attacks the bacteria. Now we've got C3b on the bacteria, we're going to be able to build our C3b BB convertase. Because we have C3b on the bacteria, which is our goal all along. So the tick-over reaction, that random flexing of C3, the random revealing of the thioester bond, once in a while that C3b will be fixed or chemically linked to a bacteria. Such as this, and now we can build the rest of the system. Okay, yeah.
So, as soon as the thioester bond is revealed, is that when the C3 becomes C3b?
I'm sorry?
In the previous slide, it shows that once C3 is cleaved, then you get C3b. So in this
No,
reaction-
okay, yeah, that's right. So that actually great catch. Is it on this slide instead?
I'm not sure
Yeah.
how it happens in this
Excellent.
slide.
It's actually, yes, thank you, good catch. I got ahead of myself. Thank you. So let me back up. Thioester bond C3 flexes, the thioester bond is revealed. The thioester bond, when revealed, creates a molecule that is C3 still, because it's not yet cleaved, that is either linked to a bacterial surface or it's bound to water and it goes away. While this is happening, there's a protein called B. B does not bind to C3. The structure of C3 is its structure, B has its own structure, they don't bind to one another. However, when C3 has either flexed to reveal the thioester bond, or when C3 has been fully cleaved to create C3b, B is attracted. So B can bind to C3b, which is the cleaved form of C3, or it can bind to the thioester revealed C3.
So this happens before or after the thioester bond attacks the bacteria?
Concurrent is the best way to think about it. I think concurrent would be the best way to think about it. So that means this picture is just a tad off, but that's okay. So B is attracted to a alternate version of C3. B can bind to C3b, or B can bind to this flexed C3 where the thioester bond has been revealed. When B is bound to the flexed, so this is the authors of this text. I don't know what text I got this from. Oh. Kubi, I think it's your text. Anyway, so when that flex C3 has occurred randomly, B binds to that C3, and now you have a molecule that is C3 flexed with B bound to it. That molecule is attracted to, is a substrate for another protease called D. So protease D will not cleave B when it's sort of floating around by itself. All these molecules are floating in your serum right now. D will not cleave B when B is floating alone. However, when B binds to C3b, or when B binds to C3 flex, one of those, And D can then use it as a substrate, and D will cleave B into BA and to BB. Now we've got a molecule that is C3 flex or C3B, BB, because B has been cleaved by D into BB. Now we have C3 flex BB, which is a convertase, but not a very good one. Or we have C3B BB bound here, because B will bind to C3B, D will cleave B, and now we have C3B BB. That's a rootin' tootin' really good convertase. So this is how we create a convertase from not having the building material to create the convertase. Yeah.
You said D isn't active until when?
D is a protease that is always biologically active, enzymatically
Or
active.
you said it won't cleave B till
It will not cleave B until B is either bound to C3 flex or to C3B. So B is attracted to C3 flex or C3B. B binds to one of those two. Now D, which is a protease, it's always active, will cleave B to create BB, so you end up with C3 flex BB, which is a convertase, but not a very good one, or C3B BB, which is bound to the bacterial surface, which is a really good convertase. So now we have created a fair quality, low quality convertase, and a high quality convertase. The high quality convertase, what's its goal? There's lots of C3 in circulation. This molecule bound to the bacterial surface is going to cleave a hell of a lot of C3. It's an enzyme. Enzymes, as you know, work as catalysts. So a hell of a lot of C3 is now going to be cleaved by this convertase bound to the bacterial surface. That C3 is going to create, by cleavage from this molecule, will create C3A, which will float away and activate phagocytes, and C3B. C3B will be revealing the thioester bond. C3B is being cleaved right near the surface of the bacteria, so C3B number 2 will bind to the bacteria. C3B number 3 will bind to the bacteria. Number 4 will bind to the bacteria because this enzyme is cleaving C3 into A and B is revealing the thioester bond binds to the bacteria. So we are fixing combo. We are covering the bacteria with C3B. We're also covering it. Each of those C3Bs we just dropped on the bacteria will bind more B, which means D will now cleave B, and we'll create even more convertase. C3B, BB, we're creating it all over the bacteria, which means even more C3. So literally, that's why I call it a cascade. That's why we all call it a cascade. But remember, enzymes are exponentially catalytically active. And although we draw this picture of bacterial surface, and you get a sense that maybe 100 molecules might cover the bacteria, the truth is you probably need 100,000 molecules of a single protein to cover an entire bacteria. How do you get 100,000 molecules of C3B on it? Well, you do the enzymatic activity of cleaving C3 into C3B, it binds to it. You add B to it, B is cleaved by D. Now you have C3B BB, which is a convertation. You've got more and more and more and more C3B all over the bacteria. You have coated the bacteria with C3B.
So can it not convert the C3 until it has BB on it?
Excuse me?
Does it not convert the C3 until it has the BB on it?
Correct. So C3, whether it's C3 flex with BB on it, or the real C3B BB is the convertase. C3 flex is not a protease. It cannot cleave anything. C3b is not a protease. It cannot cleave anything. But C3b BB can cleave C3, or C3 flex BB can cleave C3.
So the C3 flex is going to bind to a bacteria, and then the B is going to bind to that, the C3 flex bound to the bacteria?
C3 flex can bind to bacteria or can be in solution. I
Okay.
mean, remember, there's still this healthy part. You know, in healthy people, there is no bacteria, so C3
Right, but
flex
you
is
said
still
it would
made.
bind to
So
water.
we still have to deal with that. So the tick-over reaction is a random response, if you will. So we are creating C3b, C3 flex BB in healthy individuals. But luckily that is then attacked by water and it becomes useless.
So the C3
Or it
flex-
attacks water, it's a different look at water.
So the C3 flex doesn't always attack water.
It depends. If it's a bacteria, it binds to the bacteria. If you're healthy, the nucleophilic attack will be water and nothing happens.
But then if it attacks water, you can still.
Well, once it's bound to water, it's not on anything to form there's nothing to be protein with. There's no, it's sort of similar to the conversation we had about blood streams and neutrophils being washed away. I mean, you can't have an enzymatic reaction with things in liquid floating around. They've got to be at a focal site.
What I don't understand is at what point is B going to attack the C3 flex if it's always either bound to bacteria or bound to water?
So C3, I don't want to pick on you. C3b, B binds to C3 or C3 flex. C3, B doesn't attack. B can bind to C3 flex or C3b. And then that diamond, if you will, of B and C3 or C3 flex is attacked by D. So if C3 flex has no bacteria to which it's bound, B may or may not find it. Remember, it's floating around in liquid. If B finds it first, then B will be cleaved, and you create this C3 flex BB, which is a convertase, but it's floating in liquid. It's not. There's no place where it might cleave a C3, but then that floats around. Ultimately, all those diester bonds nucleophilically attack water and they're degraded. So it's really the fact that you're concentrating the enzymatic response on the surface of the bacteria that allows this to go forward. Otherwise, you're in fluid floating around in the serum, and they don't find each other. Okay? Yeah.
The C3 flex BB, like when it attaches to the bacteria, what makes it like a bad converter? Is it does the water still stay, or does it go?
Why is C3 flex BB a weak convertase? Because C3 flex still has BA
Oh, it still has that.
on it still, and it's not, the real convertase is this guy. Imagine this guy with some C3A still stuck on it. It's not as good an enzyme when some chunk of protein is still part of it.
Okay, thank you.
Okay, our goal was to create C3b. The mechanism by which we get there is this random flexing of C3 to allow B to bind to it. B bound to flex will be cleaved by D. Then you create this weak convertase, which, if you have a bacteria, will convert the C3 into C3b, which will deposit on the surface of the bacteria. That's the initiating event. This shows the same thing, so you can study off either one of these slides. But that is the initiating event of the alternate pathway. Not very efficient, not very regulated. You're relying on random flexing of C3 for this whole thing to start. That's why when you think about it, it's the evolutionary oldest part of the complement cascade. It's also the evolutionary least developed. Because it's not, it's depending on a random flexing of the C3 bond. However, once you do have some C3b, this is a repeat of what I just said, once you do have a little C3b on the surface of the bacteria because C3 flex BB cleaved a little bit of it at low efficiency, now you've got C3b on the surface of the bacteria. As I said, B is attracted to C3 flex and B is attracted to C3b. B binds to C3b. D, a protease that's always active, only recognizes C3bb. D cleaves B to create BA, BB. Now you have C3b, BB. That is the high-powered C3 convertase. Lots of C3 in serum. More C3 is converted. Now you've got this enzymatic catalytic addition of a lot of C3b onto the surface of the bacteria. And it's all happening rapidly because it's all in one place. It's not just floating around in liquid. Yeah.
So in an autoimmune disease, would the C3BB be attacking the water?
I'm sorry?
So in an autoimmune disease, would the C3BB be attacking the water? Like, would it be attacking?
So C3b, BB only exists on bacterial surfaces. Because the only nucleophilic attack on water is going to be C3 flex.
Right.
And given that thioester hypothesis. But that still doesn't eliminate your question. I just want to clean up your question. But almost all autoimmune diseases are mediated by the adaptive immune response. I can't think of any complement-mediated autoimmune disease. I can't think of any autoimmune disease that's complement-mediated. But let me double check that. There are complement diseases. Most of them are the complement system not working well, not misdirected. Okay, so now we've deposited a lot of C3b on the surface. B will be bound to C3b. B will be cleaved by D. And now you have C3b, BB. You have the convertation. That's what we want. Refresher, I'm not going to go with it. This is what I call C3 flex. There are about 7 or 8 names in the literature for C3 flex. If you get it on an exam, I'll call it C3 flex so that everyone, not the confusion, but in the textbook, if you go to different textbooks, you'll find all kinds of names in that molecule. Bottom line is the tick-over reaction allows a little breathing of C3 to reveal the thioester bond, and that breathing attracts B, and now you've got B cleaved by D, and now you have C3 bound to BB. That's a convertase. That's the alternate pathway, and notice the alternate pathway in blue. You need a bacterial surface, you need C3, you need B bound to C3 flex or C3b, D to cleave B to BB, and now you've got C3b, BB, you've got your green C3 convertase. It ends up that the other pathways are going to do the same thing with different names. There's going to be a molecule that is inert for the other pathways. That molecule gets activated by some mechanism or another, which we'll talk about. That molecule is then going to attract another protein to it. That second protein is going to bind to the used to be inert protein. That second protein is going to be cleaved by a third protein. And now you're going to have the convertase for the other systems because you've got the inert protein becoming no longer inert. You've got the protein bound to it, and then you've got cleavage of that protein, and you create C3BBB. The equivalent of C3BBB is just called C4A, C2A, C2B. So that's the parallel that I'm trying to teach. I hope it works. Inert molecule becomes non-inert, binds to the surface. Second molecule is attracted to the no longer inert molecule. It's cleaved by a third molecule, and what you're left behind with is the convertase. After cleavage of the second molecule by the third molecule. That happens in all 3 pathways, just different names. And more molecules. The more complex pathways have more molecules, but when you get through all the crap, it's an inert protein, becomes no longer inert and binds. Second molecule bind, and that's, in this case for the classic pathway, the alternate pathway, that's C3. B binds to it, that's the second molecule. B is cleaved. And that cleaved product plus the inert molecule together is the C3 convertase. Alternate pathways are a lot easier because it only has those three molecules. The inert molecule C3, the bound molecule B, the active protease D. You got much more stuff to do with the yellow and red. Okay. The classic pathway, we'll stop in a couple minutes. I'll introduce the classic pathway and then we'll revisit it. The classic pathway is the pathway in which you complement something, and you're complementing antibodies. Antibodies, you haven't had antibodies from me yet. I think we do antibodies next Monday. We'll check the schedule during the break. I'm pretty sure we'll do it next Monday. Antibodies recognize stuff. That's why we have antibodies. You all know about antibodies from your own daily life. So you don't have to know anything more about antibodies, but they bind to things. We have antibodies against bacteria, all kinds of bacteria. So the antibody, shown here in green, binds to bacteria. That's a good thing. But the antibody bound to bacteria still doesn't kill the bacteria, it might immobilize the bacteria, that's a good thing. And there are Fc receptors which we'll get to. I don't know if we ever covered it. Anyway, antibody bound to bacteria is better than no antibody bound to bacteria. So we have antibodies that recognize bacteria and bind to it, and antibodies happen to be Y-shaped molecules, don't worry about that today. So the antibodies bind to bacteria. The classic complement system has a protein complex called C1q. The C1q is a 1, 2, 3, 4, 5, 6-headed bee that binds to the non-binding, so the Y-shaped antibody. Antibodies are Y-shaped, so the ends of the Y are what recognize the bad guys, and then there's the base of the Y. The base of the Y is bound by C1q. C1q only binds to the base of the Y of an antibody when the antibody is bound to a solid surface. So antibodies float in circulation, C1q floats in circulation, they never interact with each other. Just like B and D float in circulation, they don't interact, they don't cleave each other. D doesn't cleave B because they ignore each other. It's not the right conformation. Antibodies, when bound to a solid surface, meaning bacteria, or it could be a host cell, we'll talk about that near the end of the hour, change their structure a little bit in order for this Y-shaped antibody that binds to the bacterial surface, the other end, the end is floating out, changes its structure a little after binding. That structural change allows C1q to bind to the antibody. Now all of this is happening right on the bacteria. This is why this is, if you will, a safer, more sophisticated system. We don't have any randomness now. Antibodies recognize bacteria, a good thing. Antibodies bind to bacteria, a good thing. C1q only binds to antibodies when bound to bacteria, a good thing. There's no randomness here. There's no tick over. There's no worry about nucleophilic attacks occurring in water. When C1q binds to the antibody, C1r binds to C1q. When C1r binds to C1q, C1s binds to C1r, binds to C1q, binds to antibody, binds to bacteria. Isn't there like some kid's song that says I have to put this in this one. So we're talking about small structural changes in the proteins that allow them to interact with one another. Antibodies bind to bacteria, C1q binds to the bound antibody, C1r binds to the C1q, C1s binds to the C1qr. Now we have created a molecule called C1q, it's actually two R's and two S's. We don't need to worry about that. We created a molecule C1q, R2, we'll just call them C1qRS. We created this molecule C1qRS. Where is it? It's on the bacterial surface. Our goal is to create C3 convertases that are going to cleave C3 to coat the bacteria. So all the action is already occurring right on the bacteria through the fact that antibodies bound to the bacteria in the first place. So guess what? C1QRS is going to ultimately lead to other molecules binding to it. That's going to lead to what is going to be C3 inert. It's not called C3 inert, and B bound to it. So we're going to put two more proteins, two more molecules into the picture after the break, and those molecules will be what will end up being the classic pathway to C3 conversion. So C4 and C2 are waiting in the wings, and we'll come back in 7 minutes and deal with C4 and C2. Keep remembering bound molecule, second bound molecule that gets cleaved by an active protease, and then you can create this convertase. So we're going to go pretty quick for the first 10 minutes to the next two topics. Okay, so antibody bound to bacteria, CQ bound to antibody, C1Q bound to antibody, C1RS bound to C1Q, and they only bind to each other when they're bound to their next molecule. They only bind to the previous molecule when the previous molecule is bound to a previous molecule, because there's a slight conformational change during the binding process. So now we've got the C1QRS molecule bound to antibody bound to bacteria. That's a good thing. So it ends up, this molecule called C4 only binds to C1QRS when it assembles. C1QRS only assembles when C1Q binds to antibody, blah, blah, blah. So C4 now binds to C1QRS. Ends up that R and S are proteases. So C4 is cleaved to C4A and C4B by the proteases that are RS. R and S are active proteases, but they're only active when they're bound to C1Q. So R and S are proteases, and their only job is to cleave C4. The only time they're going to be able to cleave C4 is when C4 binds to C1QRS. All other bacterial surface. C4 is cleaved, and C4 has C4A and C4B. C4A is a small little molecule, just like C3A is, and C4A is another cry for help. So it's another immune mediator that activates, that is chemoattractant for phagocytic cells, an immune mediator that binds to receptors on phagocytic cells and gets them activated. So we are getting the cellular response going while we're building this enzymatic activity. So C4A floats away and cries for help. C4B, I gotta tell you a little secret about C4B. A little secret about C4. C3 and C4 are structurally very, very similar. Let me see if you're cheap here in a minute.
Quick question before you introduce.
No. Yeah, I will. Okay. I just want to make sure that everything's consistent and nothing new has not happened. Yes.
So you said C4B is the cry for help, but then you said C4A goes off and cries for help, so I just want to make sure.
Right. So C3A, small little product of C3 when cleaved, is an immune mediator, activator of immune cells. C4 cleaves to 4A and 4B. 4A floats away and activates immune cells, just like C3A activated immune cells. C4 is structurally very, very similar to C3. What do you think C4 has? Correct. C4 has a thioester bond that is buried inside C4 that is not available in a healthy individual. What do you think happens to that thioester bond after C1 R and S cleaves C4 to C4A and C4B. Which molecule between 4A and 4B you think the thyroester bond is associated with?
B.
Perfect. What do you think happens when C4B reveals that thyroester bond? The thyroester bond attacks primary amines, SH groups. Where are their primary amines and SH groups when all this is occurring? We're already on the bacterial surface. More efficient, more controlled. That's why this system is way better than the Tickover system. C4B is going to bind to the bacterial surface through its thyroester bond, just like C3B bound to the bacterial surface. Structurally the same molecule. So what do you think C2 is equivalent to? I haven't even introduced C2 yet. You were going to tell me. C2 is the next player in this. What is C2 equivalent to compared to the first hour? B. D will only bind to C3 when C3B is bound to the bacterial surface. So C2 will bind to C4B. C2 is going to be cleaved. Is there a protease around there to cleave C2 to C2A and C2B? RNS. RNS was available to cleave C4 into A and B. RNS is still there. They will cleave C2 into, unfortunately, they screwed up. I don't know how this happened, and I never read the literature. But the big version of C2 is C2A. Really wish it was C2B, but it isn't. But guess what? We end up with a molecule that is C4B bound to C2 on the surface of the bacteria. C2 is cleaved to a big form, called C2A, unfortunately. And now we've got on the bacterial surface C4B, C4B, C2A. That is the exact same thing, structurally, as C3B, BB. We created it the same way. 2 only binds to 4 when 4 is cleaved. 2 is cleaved, and the big part of 2 binds to the big part of 4, and we end up with C4B, C2A. It is the other convertase. It's drawn like this, stylized like this, but there's a deeper message, which is structurally they are very similar, and enzymatically they are very similar. So everything I taught you was about C3B, BB, B, and D. It's all true, just call it C4 and C2. Yeah?
You said that C2 is an equivalent to B or D?
C2 is equivalent to B because C2 is going to be cleaved into a big part and a small part, and the big part, just like the big part of B, remains, and then you create the convertase right on the bacterial surface. And C2B, I don't think C2B is an immune mediator. I'm 99% sure. Just like BA, I said BA just gets cleaved and you ignore it. I'm pretty sure C2B, just ignore it. It doesn't have any biological activity. 99% sure that's true. And given the parallel, you see that BA does nothing. Parallel-wise, C2B should do nothing. And I'm pretty sure that's right. Thyroester bond, guess what? C4 has a thyroester bond that's revealed when C4 was cleaved by R and S to C4B, a thyroester bond, C4B binds, blah, blah, blah. So we create the C4B to C2A convertase the exact same way with a couple of other molecules involved. But we've got a D equivalent, that's RS. We've got a D equivalent, that's C2. We've got a C3 equivalent, that's C4. And more important, C3 has a thioester bond, C4 has a thioester bond. C2 is cleaved into a small and a large part, which has a proteolytic activity. B is cleaved into a small and a large part that has proteolytic activity. Here's our two convertases. We built our two convertases. So that's the classic pathway. Notice on the left-hand side in orange and yellow, C1q binds to the antibody, C1rs binds to C1q, R and S are enzymatically active, they're proteases. C4 comes in, gets cleaved, thioester bond gets revealed, C4 bonds to the surface, C2 is attracted, cleaved by R and S, and we're done. Yeah.
What is the advantage in all this redundancy?
Meaning, why isn't it BB? Why are we using B?
Well, you have a lot of different molecules and a lot of different pathways to do precisely the same thing.
Right. So I don't know. The reason I sort of teach it the way I do is to sort of teach you the fact that the alternate pathways are random event and very inefficient and dangerous, because once you create the C3 flex, who knows what kind of damage it might do to human cells. I like the system better because the antibodies direct all the focus of the attention right onto the surface of the pathogen. So maybe, so I don't have an answer, but I'm comfortable with the fact that the more sophisticated system needs, so the more sophisticated system, meaning the classic pathway, shares the structural homology, meaning C4b, 4a, looks a lot like BB. I'm sorry, C2a looks a lot like BB. C4a, 4b looks a lot like C3b. So I'm guessing, I'm sure, I shouldn't say this. I would bet that there was gene duplication. And C3 duplicated and created C4, and then C4 evolved to be part of the classic pathway, C3 remained part of the alternate pathway. I bet BB, the gene for B, with gene duplication created a gene for C2A, C2, and I'm guessing it's gene duplication and maybe division of labor. But beyond that, I can't help you. Okay, if we're lucky, I want to cheat. Okay. You're going to tell me, look at the lectin pathway. The lectin pathway, lectins are proteins that bind to sugar. Bacteria have sugars on them that we don't have. One of the main sugars that bacteria have on their surface that we don't have is mannose. So if we had a protein that binds to mannose, then we could initiate that same cascade I just described with antibodies with a mannose binding protein. Well, guess what? We do have a protein that binds to mannose. What do you think that protein looks like? Remember, I'm trying to build parallels here. What do you think the mannose binding protein looks like? Excuse me?
Is it like antibody?
Well, it could, but antibodies are unique structures, so it doesn't look like antibodies. But what's the next molecule? C1q. C1q is that six-headed beast, and I made a point to count 6 heads for you for a reason. The mannose binding protein looks like C1q. And guess what we're going to build? We're going to build the exact same pathway again. Mannose binding protein, the six-headed beast, which is C1q equivalent, is going to bind to the bacterial surface. It's going to attract molecules called MAS1 and MAS2. C1q attracted molecules for C1r and C1s. No difference, change in name. What do you think MAS1 and MAS2's enzymatic activity is? They're proteases. R and S are proteases to cleave C4 and then C2. So in the lectin pathway, the six-headed beast that looks like C1q is called mannose binding protein, six-headed beast. It attracts, and that MAS1 and MAS2, the P, by the way, in MAS was protease. They only bind to the mannose binding protein in yellow, when the yellow is bound to the bacteria and bound to the mannose on the bacteria. This is C12RS, except with different names. So what's going to be attracted to that? C4. So C12RS has a structure to bind C4. Mass 1 and 2 plus mannose binding protein has the same structure-ish. C4 is attracted to it. Guess what? C4 is going to be cleaved by mass 1 and mass 2 into C4A and C4B. C4A is going to float away and be an immune stimulator. C4B reveals the thioester bond. That thioester bond, remember this is all occurring on the bacterial surface because bacteria have mannose and we don't. The thioester bond of C4B will covalently link to the bacterial surface. Now we've got C4B covalently linked to the bacterial surface. C4B covalently linked to the bacterial surface attracts C2, just like it attracted it with the antibody. C2 comes in, C2 is going to be cleaved by mass 1 and mass 2. Now we've got C4B, C2A. We've got the convertase. And we've got it the same way, we just changed the names. Questions? Concerns? Issues? We're only halfway there. So we go back to this. All we've done is created C3 convertases. That was our goal, to create C3 convertases and to coat a bacteria with a lot of C3b. We've done two things. We've created C3 convertases different ways, and we've coated the bacteria with a lot of C3b. By the way, so this might answer your question, so it may not be as redundant as you think. Once C4b, C2a cleaves C3 to create C3b, which is the convertase C4a, C4b, C2a is the convertase. It cleaves C3, that's the C3 convertase, cleaving C3. CB is created or revealed, thioester bonds revealed, C3b binds to the bacterial surface. B still combines the C3b created by the classic pathway and the C3b created by the mannose pathway can still, once it's C3b, can still bind B. So now we've got two convertases on the surface. B is going to bind to C3b. B is going to be cleaved by D, even though it started with the classic pathway, or even though it started with the mannose pathway. C3b, BB is formed. That's going to convert more C3 to C3b, binds the cell, coat the cell with C3b, and create a lot of C3b, BB. So we've now got two convertases on the surface of the cell. Doesn't quite answer your question, but C3b, BB is still playing a role in all this. It hasn't gone away. And that's what this is saying. So, the mannose pathway is just like the classical pathway. A six-headed beast binds two proteases, attracts two proteases. C4a comes in, thioester bond cleaved, thioester bond, bonding to the surface. That attracts C2, thioester bond, blah, blah, blah. C2 is cleaved by the same proteases that are already there. And we've got ourselves a convertase. Now we deposit a lot of C3b on the cell, which is what this is all about. It ends up, we haven't gotten to the effector function yet. We've deposited C3b on the surface. Now we need to build the effector function. It ends up that C3b, BB, which is a convertase, or C4b, C2a, which is a C3 convertase, combine to the C3b that's already on the surface. And so you end up with C3b, BB, C3b, or you end up with C4b, C2a, C3b. C3b bound to the C3 convertase. That beast is called, it's on here, C5. C4b, C2a, C3 convertase. There's a bunch of C3b on the surface of the cell because of this molecule. So this complex formed, trimeric complex, C4b, C2a, C3b, that's a C5 convertase. C3b, bb, C3b is also on the cell, or C3b, bb is on the cell surface. More C3b is deposited on the surface, so you get C3b, bb, C3b, that is the C5 convertase. I told you that there's some memorization going on here today. At that point. What do you think C5 convertase does? It cleaves C5. And that is exactly what happens. C5 is attracted to the C5 convertase, C4b, C2a. I'm being repetitive. On purpose, I'm not. Well, I'm trying to entertain you, but I'm also being repetitive to just start giving this enough to memorize it for the exam. C5 convertase, either one of them binds C5. It's a protease. It cleaves C5 into C5a, C5b. C5a is an immune mediator. It's another cry for help. So C3a, C4a, C5a are small molecules released and available for activating cells and recruiting cells and so on. C5b, the bigger molecule, spontaneously binds non-covalently to the bacterial surface. And C5 is generated by the C5 convertase, which is the C3 convertase with an extra molecule of C3b on it, or associated with it. So what we have here is C3b, bb, C3b, the C5 convertase, C5 comes in, cleaves C5, C5a floats away, C5b binds to the surface, but is non-covalent. C5b, bound to the surface, attracts C6. C5b, C6 attracts C7. C5b, C6, C7 attracts C8. And C5b, C6, C7, C8 attracts many copies of C9. When we put all that together, C5b, C6, C7, C8, C9, together, we create something called the membrane attack complex. It is a pore. And it basically, I think I have a picture, it's the structure, it looks a lot like this. So this cartoon is kind of accurate. There's a different cartoon. Here's actually a picture of C5 of the membrane attack complex on a bacterial surface, and all these are pores. Why do we have a membrane? We need to keep the water and salt balance intact. If we punch holes in a molecule where osmotic pressure is critical, we're going to have a flood of water. There's high salt inside the cell, not much salt outside the cell. We're going to get a flood of water inside the cell through this pore. And when that flood of water goes inside the cell lyses, and the bacteria is now dead. And that's one of the four pathways, that was one of the four effector functions we were trying to achieve. The second effector function, so creating the membrane attack complex, so shown here, or shown here in the side view, shown here in the upper view, shown there schematically. The membrane attack complex is C5b, C5, C6, C7, C8, and many C9s. Forms a pore, water floods in, pops open the cell. Okay. We actually, remember there are four effector functions that that you'll be tested on, I want you to remember. The second effector function we've already dealt with. We've created C3a, we've created C4a, we've created C5a. And they're immune stimulants. There are immune mediators that are recruit and activate phagocytes. So that's the second activity of complement. It recruited and activated phagocytes by the production of C3A, C4A, and C5A. So we've got two of the four activities already here. We're doing good. So C3b, BB, is the C3 convertase. C4b, C2a is a C3 convertase. C3 convertases cleave C3 into C3b. Now we have lots of C3b on the surface of the bacteria with those convertases, and therefore we create C5 convertases. C3b, BB, C3b, and C4b, C2a, C3b. The two C5 convertases, they cleave C5, C5b self-assembles with 6, 7, 8, 9. You've got a membrane attack complex, the bacteria explodes, and we're healthy. I don't think it would surprise any of you that subhybrid groups and primary means, I said, are predominantly found on bacteria, but I don't think it would shock anyone that guess what? They're also found on mammalian cells with maybe 99% densities as they're found in bacterial cells. So there is a possibility that all of this deposition of C3b can occur on human cells. So guess what? We have an entire system to inhibit the complement system, to protect us. So the next, okay, we'll be on very much on time. We're going to finish early. The next couple of slides are introducing a whole bunch of molecules that are going to inhibit the complement system to protect human cells from being lysed by this complement system. You know, where are the other two effective ones? Why am I, do not have slides for them? Which inhibitors yeah, I don't know why I put these last. I don't know what I was thinking. I want to be finished with the other effective functions. So let me go back here. Core effective function. The membrane attack complex, we just built it. C5b, C6, C7, C8, C9, C9. The peptide mediators of inflammation. C3a, C4a, C5a. Activate and recruit phagocytic cells. So we've got these two covered. We need to cover oxidization and removal of immune complexes, and then we'll come back to the inhibitors. I don't know why I put these at the end. Oxidization is really very simple. We already discussed it in the way. Oxidization is adding spices to a bland dinner. It makes it more attractive. This is the phagocyte. There's the bacteria. Our entire goal today has been to deposit C3b on the surface of the bacteria. We did so through the CB, through the C3 convertase, and through the C, with the two different C3 convertases. So the bacteria is coated with C3b. Well, it ends up phagocytic cells have receptors for C3b. It's called CR1, doesn't matter. And therefore, just like adding spices to food makes it more attractive, since we have receptors for molecules that are now coating the bacteria, the chances of phagocytic cell finding a bacteria and phagocytosing it and destroying it is much higher now that we have fixed complement, we have coated the bacteria with C3b. That's oxidization. We increase the efficiency of phagocytosis by coating the bacteria with C3b because we have C3b receptors on phagocytic cells. Good? That's the third effector function for the complement system. And the fourth effector function is removal of immune complexes. immune complex, so the middle, no, that's not good, yeah. The middle of this, well, the immune complexes, oh, sorry, I didn't see the top. Immune complexes are when antibodies and antigens form a very large structure. We will spend time on Monday, actually we'll play some games on Monday, or I think I'm coming back Monday, in which to explain what immune, actually that's not true. I do that in the hypersensitivity class and I'm not teaching hypersensitivity. So we're not going to play a game. Maybe you can convince the person who does hypersensitivity to play a game with this. Anyway, immune complexes are foreign chemicals bound to antibodies such that they form a very large structure. Chemically, very, very large structures are insoluble, and they fall out of solution. So an immune complex, when it grows big enough, will fall out of solution. If it falls out of solution in your brain, or in your kidney, or in your liver, you're in big trouble. If you're going to have kidney disease, liver disease, or neurological disease. Because the immune complex is now, you've got this insoluble mass stuck somewhere in the filtering part of the kidney, or the filtering, or the tubules of the liver, or in your brain, causing potentially blood vessels and creating strokes, and on and on and on. So, immune complexes need to be removed. Remember the classic pathway. C1q will bind to antibodies. The antibodies bound to bacterial surfaces. If the immune complex is big enough, not reaching the size of a bacteria, but big enough for C1q to be attracted to the antibodies in that immune complex, then C1q binds to the antibodies in the immune complex. C1rs are brought in. We build the C4A, C4B, C2A, C3 convertase right on the surface of the immune complex rather than on the surface of the bacteria, but conceptually it's the same thing. It's a big molecule that shouldn't be there. We deposit C3b on the surface of that immune complex because C3b will covalently link to primary amines and SH groups. Now we've got C3b coating the immune complex. We have receptors for C3b, we just talked about for opsonization. And therefore, the immune complex will bind, a lot of times, it binds to erythrocyte, and then the erythrocytes are small compared to the size of a phagocyte. And then their phagocytosis, but it doesn't matter. The fact that we've got these immune complexes that are large structures that we don't want, they're coated with C3b, and therefore they're going to be removed by phagocytosis. That's the fourth effective function of the complement system. Okay. I shouldn't put this. I'm going to change things up. What are we doing on time? I'm going to summarize, then we'll move to inhibitors. 3 pathways to active are the end game is these 4 effective functions. The mechanism to get there is to create this molecule with C3 convertase. We get to C3 convertase, we can create the terminal attack complex, the membrane attack complex, we can create those immune mediators, we can create the opsin pathway. So creating C3 convertase is the key to this. It's sort of the focal point for the entire pathway. 3 pathways lead in, and 4 effective functions come out. Okay? If you were going to create inhibitors of this system, what would you try? What's the best place?
C3 conversion.
Right. C3 is a focal point. If we can't create C3, or if we cause C3 to be inactive, none of this happens. So to inhibit the complement pathway, there are a lot of inhibitors that target C3. There are some inhibitors that don't, we'll talk about them briefly, but the vast majority target C3. What's the slide? That's this, those are the C3 converters. Well, how would you design an inhibitor to inactivate them?
Something that targets sulfide bonds.
Something that targets these convertases, true, and then how would you target them? What would you do to inhibit them? What's the fastest way to inhibit them?
I would compete with BB or C2A.
Right. Separate those molecules. If we can drive a wedge between 2A and 4B, or if we can drive, I never said that 2A and 4B were covalently bound, and they aren't. I never said that BB and C3B are covalently bound, they're not. So if we can drive a wedge between those molecules, we kill C3, we shut off the complement system. And the series of inhibitors we're going to talk about now, the vast majority do just that. It's going to take me an hour to get to them, but they already do. This inhibitor doesn't do that, so that's sort of why we're skipping, and I may come back to it or may not. Dissociation of the convertase. One of these is C3b-BB, and one of these is C4b-C2A. If we cause them to separate apart, we've inhibited complement. And look at the number of molecules that we have that cause this dissociation. Those are the molecules that are involved in regulating the complement system to protect the host from this very dangerous. You figure out the system, there's no specificity in the system at all. The only specificity is a SH group or a primary amine, and that's not very high specificity. So the host is a real likely target for this cascade, and therefore we need something to, we need a lot, 1, 2, 3, 4, 5 different molecules to dissociate that convertase to minimize its damage to host. Where would you put these inhibitors, these dissociation molecules? Our goal is to protect the host, but we don't want to shut the whole complement system down because then you have no protection. So where would you express those molecules? Where are you going to find them? It's sort of a trick question. What's the answer?
I suppose anywhere that C3 could be, right?
Excuse me?
Anywhere that C3 could be, you'd want these also?
Anywhere where C3b can deposit, right, so that would be C3 mostly deposits on the surface of pathogens, but it could potentially deposit on the surface of the host cell, and we certainly wouldn't want that. So that's a good beginning. So where would you guys put some of these inhibitors?
Cell surface?
Right. So human cells express DAF and MCP. MCP and DAF are cell-bound surface proteins. So if a little C3b ends up on the surface of a human cell, B will be attracted. B will be cleaved to D, by D to C3b-BB. DAF and MCP will dissociate C3b from BB, and you've shut down the complement system that is about to kill the human cell. Ends up, we also put these in circulation. I'm a little less comfortable with the, factor H is a soluble molecule, it's not a surface-bound molecule. So I'm not quite sure why we put them in circulation, I'm a little troubled by that, but they're in circulation nonetheless. We have a second mechanism, which is on this slide and probably on the next slide too. from the next slide as well. Where not only do we want to dissociate these convertations to make sure that they are inactive, but if we dissociate them, we're dealing with enormous numbers of molecules floating around. So how do we assure that they don't reassociate? You know, the C3b from over here on the left-hand side of the bacteria and the BB from the right-hand side of the bacteria might find each other someplace else on the bacteria or whatever, and the bacterial surfaces are mobile just like human surfaces are mobile. So there's a possibility they might reassociate. So the extra piece to this puzzle is there's a protease called I, which actually cleaves. So we have all of these molecules here that cause the dissociation of C3 convertase and C5 convertase. And then we sprinkle in a little protease called factor I that cleaves the dissociated molecule. Now you've dissociated them and cleaved them, the problem is solved. And that's what this is showing. Sadly, but good for you guys. It ends up, and I'm just going to tell you because it would be not right to tell you, but we're not going to deal with it. It ends up that with this proteolytic cleavage by factor I, we create something called C3C and C3D and I-C3B and a whole bunch of molecules because we're cleaving. Each of those have biological activity as well, but not for today. All we're going to do today is dissociate the convertases, cleave them with factor I, and we're done. But, just so I have told you once, but ignore it, the products of those cleavages also do things. All right, so I think I've covered. Yeah. There is a little specificity, not to be memorized, but just so you know that some of these dissociation molecules work better to dissociate C4B, C3, C2A. Some of them work better to dissociate C3B and BB. I'll show you. But you don't need to know who does what, and actually I don't know who does what. I have to look it up each time. I mentioned that the cleavage products, there are lots of cleavage products, they have biological activity, don't worry about what that activity is. And then there are a couple of inhibitors that I skipped. Because the message for me, at least, in my mind, is inhibitors that work on that central focused convertase are conceptually the most logical inhibitors to design. It ends up, we also have an inhibitor called C1 inhibitor, which prevents, remember C1q, once bound to an antibody, attracts C1R and C1s. The C1 inhibitor prevents RNS from binding to C1q. So therefore, the initiation of the classic pathway doesn't occur when the C1 inhibitor. We also have a C4, we have a C4 binding protein. So even though C4b is listed here as a dissociation, that's really not accurate. C4b binds to C4. C4b binding protein binds to C4b and prevents it from having proteolytic activity. It's not dissociating C4b from C2a, but it is an inhibitor of C4b's pathway. And I think we should probably stop. This slide covers, oh, we have inhibitors in the macron. Yeah, so we have inhibitors of preventing C4RS from binding to C2. We have inhibitors that bind to C4b and prevent it from being proteolytic activity. We have dissociation molecules that separate the convertase into individual parts, and then we have factor I that cleaves all those molecules so they're inactive as a convertase. And We also have inhibitors that are found on the cell surface and in solution both that inhibit the membrane attack number. So the number of inhibitors, is it here? No, maybe I thought I had a slide. Yeah. These are all the molecules that I mentioned today. The ones you really want to worry about are the ones you spend an hour and a half on. The ones you want to be aware that exist are the ones you spent the last 3 minutes on, which are the inhibitors listed here. And the complement receptors are the mechanism by which opsonization occurs. Remember, C3D binds to the bacteria, makes it more tasty, and that tastiness is because there are receptors for the C3D on cells. And then all the molecules from purple and above are molecules we talked about in detail for the hour. I think we'll stop. I'll hang around for a couple minutes.